We can now take the last step of our path and study systems of particles where there is potential energy associated with interaction and include Einstein's rest energy in the law of conservation of energy. Is it possible to generalize the law of conservation of energy, including rest energy? As we know, for an isolated particle, the total energy is the sum of its kinetic energy, gamma minus 1 times mc squared, plus the rest energy, E0, equals mc squared. But what if the particle is not isolated and there are interactions? Experimentally, it's been established that a generalization of the law of conservation of energy holds, including rest energy. This means that, experimentally, for an isolated system of interacting particles, we have that the rest energy plus the kinetic energy plus the potential energy is equal to a constant value. Now, an interaction where the particle's identity is preserved, the rest energy is simply an identical additional term on both sides of the energy equation, and it simply cancels out. The importance of including the rest energy in the energy law appears in interaction among particles that change their identity. A case in point to illustrate the importance of including rest energy in the conservation law is the free neutron decay, il decadimento del neutrone libero. Now, outside the atomic nucleus, a neutron is an unstable particle that decays into a proton after a mean life of about 15 minutes, changing its mass and therefore changing its rest energy. Here it is the reaction that takes place. We have a neutron which decays into a proton plus an electron and a tiny particle called antineutrino, which is almost massless, therefore it has almost zero rest energy. Now, if we compute the rest energy for each one of these particles involved, we get 939.6 megaelectron volts for the neutron, 938.3 megaelectron volts for the proton, and 0.511 megaelectron volts for the electron. And if we add up these two terms of the particle resulting from the reaction, do not forget that the antineutrino has zero rest energy, we get a number that is less than the initial 939.6 megaelectron volts. Therefore, there are 2.2 megaelectron volts that the three particles originated must have in form of kinetic energy. Therefore, even if the initial neutron was standing still, the emitted particle must be moving after the decay. So, if we want the law of conservation of energy to be satisfied, we have to equate the rest energy of the initial neutron to the sum of the rest energy and kinetic energy of the proton plus the rest energy and the kinetic energy of the electron plus the kinetic energy of the antineutrino. What is the mass of a system of interacting particles? Let's consider a system of interacting and moving particles, which is at rest as a whole, namely its center of mass is at rest. We can look at the system's mass as a whole from two different viewpoints. On one hand, according to the theory of relativity, if the overall mass of the system is m, the rest energy is E equals mc squared, namely the mass is related to the rest energy. But since the system as a whole is at rest and it is not interacting with other bodies, the rest energy corresponds to the total energy. On the other hand, we can get the system's energy by adding up the energies of its constituent particles. Therefore, we have that the energy of the system is given by adding the rest energy of the first particle with the kinetic energy of the first particle plus the rest energy of the second particle plus the kinetic energy of the same particle, and so on and so forth, plus the potential energy of the particles. And if we equate these expressions for the energy of the system, we have a relation which gives the mass of the system as a whole as a function of the masses of the individual particles, their potential and kinetic energies. And if we separate into two parts this fraction, in the first part we can factor out c squared and cancel it off with the denominator, we get an expression for the overall mass of the system, where it is clear that m is not equal to the sum of the particle masses, but it can be greater or less than m1 plus m2 plus m3 and so on, depending on the sign of these terms containing the sum of their kinetic energy and potential energy. As a result, the internal energy of a composite body affects its mass. For instance, a box containing some ideal gas is more massive when heated because its mass is the sum of the individual particles' masses plus their kinetic energies divided by c squared. Since it is an ideal gas, we have no potential energy contribution in this case. Anyway, the difference between m and the sum of the individual particles' masses is negligible at non-relativistic speeds, where the kinetic energy is too small to make a significant change in the mass, and in chemical bonds and reactions where the potential energy is too small to make a contribution to the mass, which is not negligible. However, U is not negligible when nuclear reactions take place. In this case, because of the considerable amount of the potential energy U involved in a nuclear reaction, a difference between the system's mass and the sum of its particles' masses is observed. However, do not forget that the potential energy is defined only up to an arbitrary constant, namely we have to define the 0 point of the potential energy. Does this mean that when we change the 0 point, the system's mass changes? Namely, if we change the 0 point, the value of U over here changes and mass changes in turn. Now, to get the reason why this is definitely not the case, we need to remember that only potential energy differences delta U have physical meaning. And if we want the value of U to have a physical meaning too, we cannot assume that U is equal to 0 in a configuration of our choice. We must assume that U is equal to 0 in a configuration where the system is not capable of doing any work because of the spatial distribution of its particles. And this happens only when particles are infinitely far apart and there is no interaction among them. Therefore, we will assume that U is equal to 0 when the particles of the system are infinitely separated in space. It is only by this choice that U assumes the physical meaning of work that the system can do because of its spatial configuration, and there is no more ambiguity in the definition of mass in this formula. We'll now apply Einstein's theory to chemical bonds and chemical reactions. As a case in point taken from chemistry, we'll now consider the mass energy of a diatomic molecule at rest. A diatomic molecule is a molecule made up of two atoms of the same element, for instance the hydrogen H2 molecule, which is made up of two atoms of hydrogen, or the oxygen O2 molecule, or nitrogen N2. We can think of this molecule's mass energy in two different ways: as the sum of two individual atoms' kinetic and rest energy. Here we denoted by m the mass of every single atom and by k their kinetic energy, plus their potential energy of interaction. But we can think of the molecule's mass energy also as the rest energy of a system having mass m and which it is at rest as a whole and not interacting with other systems. Therefore, the rest energy is m times c squared, but it corresponds to the total energy of the system since there is no other contribution coming from kinetic or potential energy. Since these two values must be equal, we have mc squared equals to 2mc squared plus k plus the potential energy. Let us consider the potential energy for the system of a diatomic molecule in more details, assuming that U is equal to 0 when the two atoms are infinitely far apart and there is no interaction. Here we have the mathematical behavior of the potential energy as a function of the distance between the two atoms. As you can see, U goes to 0 as the distance approaches infinity. But we have a more interesting behavior in the region of distances less than R0, where the negative slope we observe has the physical meaning that the two atoms repel if they are pushed together at these very short distances. We also got a positive slope region, which has the physical meaning that when the two atoms are separated at distances greater than R0, they attract. Therefore, the system has an equilibrium point with negative potential energy at R0. And this means that the potential energy for this system in equilibrium is negative, and therefore it gives a negative contribution to the molecule's rest energy. And this makes mc squared less than the sum of the two atoms' individual mass multiplied by c squared, since the U term is negative. The molecule's rest energy is also slightly increased by the two atoms' positive kinetic energy contribution, namely, the two atoms in the molecule are not standing still, but they have some sort of vibration of some kind, and this gives a positive contribution to the mass. Therefore, in every diatomic molecule chemical bond, 2mc squared is the sum of the individual atoms' rest energies when they are infinitely far apart. This value is decreased because of the negative potential energy contribution. This graph is not to scale, since 2mc squared is much greater than typical energies value for U and K, and it is also slightly increased by the two atoms' positive kinetic energy contribution. Therefore, we get an equilibrium energy value mc squared, which is the rest energy for the molecule as a whole, which is slightly less than the sum of the two individual atoms' rest energy. This means that when a diatomic molecule is created, some energy, namely this difference, must be given off by means of emitting photons. To illustrate this point, consider that when an hydrogen molecule H2 is created, 4.52 electron volts are given off. When an oxygen O2 molecule is created, 5.15 electron volts are given off in form of emitting photons. And when nitrogen N2 molecule is created, 9.79 electron volts of energy are given off. And the same amount of energy is required if one wants to split the molecule into its constituent atoms, and this is called the binding energy, che in italiano si traduce con l'energia di legame. However, in chemical bonds, the ratio between the binding energy and the rest energy of the constituent atoms is really tiny. Let's evaluate this ratio for a diatomic molecule of hydrogen, which contains two products. The numerator is the binding energy of the molecule. The denominator is the proton rest energy. We have 4.52 electron volts over 938.3 millions of electron volts, or mega electron volts, and this gives 4.81 times 10 to the minus 6, almost 5 parts in a million, so it is too a small effect to be detected in everyday phenomena. Nevertheless, any form of energy possessed internally by a body composed of several particles changes its rest mass. Kinetic energy always increases the body's rest mass, since it is always positive. As for potential energy, it can decrease the body's rest mass, as it is the case for chemical bonds, but it can also increase the body's rest mass when it is positive, as when we compress a spring. Therefore, a hot block of iron possesses more rest energy than the same block when it is cold, because of the kinetic and potential energies of its particles. Of course, the effect is too small to be measured in everyday phenomena, but energy possesses inertia. And what about nuclear bonds and nuclear reactions? Well, the kind of potential energy stored in the system's particle is not important. We have lots of everyday processes which transform tiny amount of mass into energy. Processes like dynamite or fire. To illustrate this point, consider that an explosion of 1 kilogram of TNT releases by means of a chemical reaction 5 times 10 to the 6 joules, 5 millions of joules, which by the way corresponds to a very large number if transformed into units for energy on the atomic scale, but in mass corresponds only to 6 times 10 to the minus 11 kilograms. The difference between chemical reactions and nuclear reactions with respect to the transformation of mass into energy is only a quantitative one. In chemical reactions, there are only rearrangements of the outer electrons in the atoms. The force involved is the electromagnetic force, and the energy released in one reaction is of the order of few electron volts. Of course, if you multiply this energy by amount of masses on the scale of the object, you get large numbers. In nuclear reactions, the strong nuclear force is involved, and it has a huge potential energy. Therefore, the amount of mass into energy transformation in one reaction is of the order of some mega electron volts. Therefore, an explosion or a reaction of 1 kilogram of uranium releases 1 million times this quantity. What is the strong nuclear force? It is what we could call the nuclear glue. It's a strong attraction that prevents protons in the nucleus from repelling each other because of their electrostatic repulsion. But it acts only when protons and neutrons are very close. If protons and neutrons were objects, we would think of the strong nuclear force as a sort of action that requires contact. Here we have the nucleus of helium-42, namely a substance which has 2 protons in its nucleus and 4 nucleons. We have electric repulsion between the 2 charged nucleons, but there is also a strong nuclear attraction between them, and since the nuclear attraction between 2 protons in the nucleus is approximately 100 times stronger than their electric repulsion, it prevents the nucleus from splitting. However, the nuclear attractions is not only between the 2 protons but also between one neutron and the other, and between each neutron and each proton. To the strong nuclear force corresponds a large binding energy, namely the amount of energy required if one wants to split the nucleus molecules into its constituents is very large. In which way do nuclear reactions liberate energy? The mechanisms that makes it possible to release energy in nuclear reactions is the difference in the average binding energy per nucleon in the elements, la differenza nell'energia media di legame per nucleone, sia esso un protone o un neutrone. Here we have a plot of the binding energy per nucleon in megaelectron volts as a function of the nucleon number, and a sample of the elements we find in nature: hydrogen, helium, lithium, carbon, nitrogen, iron, krypton, barium, and uranium. As you can see, in iron, which has 26 protons plus 30 neutrons, which is equal to 56 nucleons, we have the largest binding energy per nucleon, namely 8.6 megaelectronvolts. The largest binding energy means the most negative nuclear potential energy, since these two quantities are opposite. This means that we must provide 8.6 megaelectronvolts per nucleon if we want to split a nucleus of iron. The binding energy per nucleon increases as the number of nucleons increases from 1 up to 56, and then it slightly decreases. This means that, in principle, energy can be gained in two ways: by means of the fusion of two small nuclei lighter than iron into a larger one, or by splitting up one large nucleus heavier than iron into a smaller one. Indeed, either in fusion or in fission, the nuclear potential energy per nucleon becomes more negative. Therefore, there is a difference in energy which must be given off in both processes, and this energy can be harnessed. What is the reason for such a behavior of the binding energy in nuclei? Consider a nucleus of nitrogen which has 14 nucleons, among which 7 protons. As we know, only adjacent nucleons attract. Therefore, we have attraction among these nucleons, or among these, or among these. But all protons repel, even if they are not contiguous. Therefore, we have electrostatic repulsion between two protons like these, or between these two protons, or between these two. Let us consider now surface nucleons like this, 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 this. A surface nucleon is not completely surrounded, therefore it experiences nuclear attraction only from one side, and as a result it is less tightly bound with respect to a nucleon in the inner part of the atom. Now, when the overall number of nucleons increases, as in potassium 39, K is from the Latin word for potassium, kalium. The volume of the nucleus, which is approximately a sphere, increases as the third power of the radius, whilst the surface of the sphere increases as the second power of the radius. Therefore, the volume of the nucleus increases more than its surface. And this means that a stronger binding is achieved, since we have a greater fraction of nucleons which is completely surrounded. And this explains this part of the curve. But when the number of nucleons grows and it reaches values as large as 56, what happens is that the number of protons is greater. Therefore, the overall repulsion among protons is greater. But each nucleon has always more or less the same number of contiguous particles. so that, in spite of the fact that the overall number is growing, nuclear attraction remains constant, since it is exerted only by contiguous particles. Therefore, since electrostatic repulsion is growing, but nuclear attraction remains constant, when the protons overcome this number 56, their repulsion becomes effective in reducing the binding energy, and this explains the decreasing of the binding energy on this side of the plot. Therefore, for atoms with nucleon number less than 56, the fraction of surface nucleons decreases because the nucleus volume increases more than its surface, and this produces a stronger binding. On the contrary, for atoms with nucleon number greater than 56, the electrostatic repulsion between protons increases because the number of protons increases, but the nuclear attraction remains constant because the number of contiguous particles is always the same, and nuclear attraction is only due to contiguous particles. It is a contact action, and this produces a weaker binding on this side. So, what happens when the nuclei of elements lighter than iron fuse together? Nucleons in lighter elements like hydrogen or helium or lithium are less tightly bound than in iron, namely, they have less negative potential energy, which is the opposite of the binding energy shown here. Therefore, they have the possibility to fuse together and form heavier nuclei. We call this phenomenon nuclear fusion. And it is precisely what happens in the interior of the Sun. Stars are fueled by hydrogen nuclei that fuse together to form helium, whose nuclei in turn fuse to form carbon, and so on, stopping at iron. In stars with a core temperature not greater than 15 million kelvins, hydrogen fusion takes place by means of the so-called proton-proton chain, which is a process where 4 hydrogen atoms are involved to create one helium atom by means of several intermediate steps which are not shown here. This reaction yields 26 megaelectron-volts in energy. The energy is released in the form of electromagnetic radiation, namely gamma rays, neutrinos and positrons, and kinetic energy. And the released energy raises the temperature of the interior of the Sun and supports it, preventing the star from collapsing under its own weight. What happens when the nuclei of elements heavier than iron split into fragments? Let us consider uranium, whose nucleons are less tightly bound than in lighter elements. We have 1 megaelectron-volt difference with respect to the average binding energy in iron, and since every uranium atom has more than 200 nucleons, in each single splitting reaction it is able to give off up to 200 megaelectron-volts in energy. Nuclear fission is achieved in reactors by bombarding a uranium-235 nucleus with slowly moving neutrons. Whereas fast-moving neutrons bounce off the nucleus, slowly moving ones are captured and make the nucleus split into 2 fission fragments and 1 or more neutrons. When the additional neutron enters, it changes the nucleon's spherical shape into a 2-lobed form similar to a peanut, increasing the occupied volume. Also, 177 megaelectron volts are released of the order of 200 megaelectron volt, as we said before. Now, this change in shapes increases the volume occupied, and therefore the electrostatic force overcomes the attraction, which is short range, and makes the fragments accelerate and reach very high speeds so that they hit the block of uranium. There is not just one single fission reaction involving uranium, but many different fission reactions are possible, and many different fission fragments are possible too. Here we give an example of reaction that produces barium and krypton. An atom of uranium-235 plus one slowly moving neutron splits into barium-144 plus krypton-89, which are called fission fragments, plus 3 neutrons, and 177 megaelectron volts are given off in form of kinetic energy of the fission fragments and the neutrons, plus electromagnetic radiation. Note that the number of nucleons is the same on both sides. 235 plus 1 is equal to 144 plus 89 plus 3. In this equation we get 236 on both sides, but the rest masses on the right are smaller by a factor of 177 megaelectron volts over c squared. These fission fragments and the neutrons are moving at fast speed, and they hit the block of uranium. When many fissions take place, the temperature of the uranium increases. It can get up to about 600 degrees and becomes enough to make water boil, producing steam to power a turbine in an electric generator. Therefore, in the end, what you do in a nuclear power plant is to get some water to boil. We'll end our series of lessons reading a famous letter wrote by Albert Einstein to the President of the United States, Franklin Delano Roosevelt, in 1939 on the atomic bomb. Sir, some recent work by Enrico Fermi and Leo Szilard, which has been communicated to me in manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness and, if necessary, quick action on the part of the administration. I believe, therefore, that it is my duty to bring to your attention the following facts and recommendations. In the course of the last 4 months, it has been made probable, through the work of Joliot in France as well as Fermi and Szilard in America, that it may become possible to set up a nuclear chain reaction in large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. Now, it appears almost certain that this could be achieved in the immediate future. This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of new type may thus be constructed. A single bomb of this type, carried by boat and exploded in a port, might very well destroy the whole port together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air. The United States has only very poor ores of uranium in moderate quantities. There is some good ore in Canada, in the former Czechoslovakia, while the most important source of uranium is Belgian Congo. In view of the situation, you may think it desirable to have more permanent contact maintained between the administration and the group of physicists working on chain reactions in America. One possible way of achieving this might be for you to entrust with this task a person who has your confidence and who could perhaps serve in an unofficial capacity. His task might comprise the following: to approach government departments, keep them informed of the further development, and put forward recommendations for government action, giving particular attention to the problem of securing a supply of uranium ore for the United States. To speed up the experimental work, which is at present being carried on within the limits of the budget of university laboratories, by providing funds, if such funds be required, through his contacts with private persons who are willing to make contribution for this cause, and perhaps also by obtaining the cooperation of industrial laboratories which have the necessary equipment. I understand that Germany has actually stopped the sale of uranium from the Czechoslovakian mines, which she has taken over. That she should have taken such early action might perhaps be understood on the ground that the son of German Under-Secretary of State von Weizsäcker is attached to the Kaiser Wilhelm Institute in Berlin, where some of the American work on uranium is now being repeated. Language of learning. You say massless, privo di massa. The neutrino is an almost massless particle. A particle can decay into others. The free neutron is unstable and decays into a proton, an electron, and an antineutrino. A quantity can be negligible. The difference between classical mass and relativistic mass is negligible in chemical bonds. A quantity can be defined up to an arbitrary constant. The potential energy is defined up to an arbitrary additive constant. Particles can be infinitely far apart. We choose the 0 point of the potential energy in the configuration where the particles are infinitely far apart. Language of learning. You say a chemical bond. A chemical bond is an attraction between atoms that allows the formation of chemical substances. You say not to scale. The figure is not to scale, namely it does not show proper proportions. You say that energy can be given off. When a diatomic molecule is created, some energy must be given off by means of emitting photons. You say average. The average binding energy per nucleon. You say bond, binding, bounded. A chemical bond or the binding energy. Language of learning. You can equate two expressions. Equating these two expressions we get, you say by times multiplied by 3 by 4, 4y, 4 times y. You say fission, in italiano fissione o più propriamente scissione. You say made up of, a molecule made up of 2 atoms. You say because of, the work that the system can do because of its special configuration. language of learning. You say the behavior of a function, l'andamento di una funzione riferito al suo grafico. The behavior of the potential energy has a minimum. You say to split into. Uranium splits into fission fragments.